So let's start with the third part, the final part of the variational autoencoder. Now in this, you have to learn the generate samples. Now in this updated code, we redefine the latent samples variables with a shape of 5 latent dimension, allowing it to generate 5 random samples instead of 10. We also modified the for loop to iterate 5 times, displaying 5 generated samples instead of 10. Additionally, we adjust the subplots include a function to arrange the generated samples in a grid with 1 row and 5 columns. Generate sample is the code for that. Generate samples. Latent samples is equal to TF random normal. Shape is equal to 5 latent dimension. Then generated samples is equal to decoder latent samples. Then plot the generated samples. Import matplotlib iplot as PLT, and for I in range 5 PLT subplot 1 comma 5 comma I plus 1, and then plot. So this is simple code for generating the plots. The output can be like this. When you run this code, it will generate a figure showing these images that resemble the ones from the MNST test set. The system will display these photographs in a grid arrangement featuring 1 row and 5 columns. The system will showcase them in a gray scale using the gray color map without text axis. Visualization of latent space. To gain insights into the latent space of VAE, you can follow these steps. Utilize the VAEs to encode the training data points, projecting them into latent space. Employ a dimensionality reduction techniques like TSNE, T-distributed stochastic neighbor embedding is an unsupervised non-linear dimensionality reduction technique for data exploration and visualization high-dimensional data. Non-linear dimensionality reduction means that the algorithm allows us to separate data that cannot be separated by a straight line. To map the high-dimensional latent space into 2D space suitable for visualization. Third, the plot the data points in 2D space, allowing a visual exploration of the latent space. The following process can effectively visualize and comprehend the underlying structure of the distribution of the latent space in the VAE. Again, is a code for that. Import TensorFlow STF from sklearn manifold. Import TSNE. Latent vector is equal to encoder extrain numpy. Latent 2D, that is TSNE, and component is equal to 2. Fit transform latent vectors. Then plot. Third is plotting latent space. PLT scatter latent 2D, comma 0 latent 2D is equal to y plane map is equal to VAE distribution, and then plot code bar and plot show. So this will show the plot. How VAEs could be used in the future. Personalized medicine. VAEs could be used to develop personalized medical treatments for patients based on their individual genetic makeup and medical history. For example, it could be used to design new drugs that are more effective and more pure and have fewer side effects. New materials. VAEs could be used to design new materials with unique properties, such as stronger and lighter materials, or aircrafts, or more efficient solar cells. For example, it could be used to design new materials that can withstand extreme temperatures or pressures. Creative AI, VAEs could be used to create new forms of art and entertainment, such as realistic images, videos, or music that is tailored to a user's individual preferences. For example, it could be used to create new video games or movies that are more immersive and engaging. Scientific research, VAEs could be used to generate new scientific data for research purposes. For example, it could be used to generate new images and galaxies or proteins to create new simulation of physical systems. Conclusion. A variational and autoencoder is an enhanced form of an autoencoder that incorporates regularization techniques to mitigate overfitting and ensure desirable properties in the latent space for effective generative processes. Functioning as a generative system, VAEs share a similar objective with generative adversarial networks like a conventional autoencoder. A VAE comprises an encoder and a decoder. Its training aims to minimize the reconstruction error between the encoded and decoded data and the original input. Points to remember, variational autoencoder can learn to reconstruct and generate new samples from a provided dataset. By utilizing a latent space, VAEs can represent data continuously and smoothly, facilitating the generation of the variation of the input data with smooth transitions. The architecture of VAEs consists of an encoder encoder network that maps the input data to the latent space. A decoder network responsible for reconstructing the data from the latent space, and a loss function that combines a construction loss and a regularization term. VAEs have demonstrated their utility in image generation, anomaly detection, and semi-supervised learning tasks. Important questions. What exactly is a variational autoencoder? The variational autoencoder VAEs are probabilistic generative models with a different components, including neural networks called encoder and decoder. The encoder network handles the first part and the decoder network handles the second part. Advantage of VAEs. One of the main benefits of VAEs is their ability to generate new data samples that closely resemble the training data achieved through the continuous latent space, enabling the decoder to produce new data points that smoothly interpolate between the existing training data points. What is the most crucial drawback of VAEs? A notable limitation of variational autoencoder is their tendency to produce blurry and unrealistic outputs. This issue arises from their approach to recovering data distribution and calculating loss functions. Which is better, GAE or GAN or VAE? GANs produce highly realistic images that can be challenging to train and work with. On the other hand, VAEs are generally easier to train but may not always achieve the same level of image quality as GANs. Thank you.